In industrial maintenance, there is a common paradox. Production targets increase, equipment ages, and the maintenance backlog grows week by week. You might assume the only solution is to hire more technicians, but there is a way to gain the output of 5 extra people without adding a single name to the payroll. To find those hours, we have to look at how maintenance time is actually spent. In an unstructured operation, technicians are constantly delayed by missing parts, vague instructions, and shifting priorities. Because of this friction, their productive wrench time, the actual time spent fixing equipment, usually sits between 25 and 35% of their shift. The rest of the day is consumed by logistical waste. This chart illustrates the planner leverage principle. It compares the industry average wrench time of 25 to 35% against a world-class target of 55 to 65%. If you take a team of 15 unstructured technicians and convert one of them into a dedicated planner, you remove the daily friction. The remaining 14 technicians can now work at 50% capacity. That smaller group now produces the equivalent output of 19 unstructured technicians. Reaching that level of efficiency requires 2 non-negotiable prerequisites. First, you need a functioning CMMS platform, like SAP or Maximo, where every piece of data is tracked. Second, you must establish that dedicated maintenance planner role. Without those 2 elements in place, the friction remains. When you look at the numbers, a sprawling maintenance backlog is rarely about a lack of staff. It is the result of how existing hours are structured. By implementing disciplined work management, you recover hundreds of hours of hidden capacity. That capacity becomes accessible through a specific operational engine, the 6-step work management cycle. It is a continuous loop designed to convert reactive chaos into predictable output. Step 1 is identify. Every potential issue must be captured as a notification in the system immediately. Work does not exist unless it is in the CMMS. Once identified, each request is strictly prioritized based on the criticality of the equipment. A critical production asset gets a different priority code than a general service pump, ensuring the most important issues route to the front of the line. Step 2 is plan. This acts as a strict gate for all incoming work. Planners must validate the exact scope of the job, outline the safety requirements, and confirm that all necessary parts are physically available. A work order cannot pass this gate and become ready to schedule until every resource is confirmed. Step 3 is schedule. You assign a hard limit of 80% of your available labor capacity. The remaining 20% is intentionally left unassigned. This buffer absorbs the urgent, reactive breakdowns that will inevitably occur, protecting your planned work from being derailed. Step 4 is execute. With the schedule locked, the shift begins. Here, the supervisor's role shifts away from scrambling for parts. Instead, they spend their time on the floor, supporting the technicians and performing quality over-inspections to ensure the work meets the required standard. Finally, steps 5 and 6 are close out and analyze. A completed repair is useless to the system if the paperwork is ignored. Technicians must log their actual hours, any delay codes they encountered, and the specific failure feedback. That data flows directly back into the system, closing the loop and allowing engineering to eliminate future defects. These 6 steps must happen in exact order. Skipping the planning step to rush a repair or ignoring the closeout data degrades every subsequent cycle. The moment you shortcut the process, you slip right back into firefighting mode. To protect those 6 steps, you have to map them onto a rigid Monday to Friday timeline. This weekly rhythm must be treated with the exact same strictness as a production shift schedule. Monday and Tuesday are focused heavily on execution and review. The team analyzes the previous week's performance data, reviews the current backlog, and works to clear out the immediate P1 and P2 reactive threats. Handling these safety and production-critical issues early creates breathing room. By Wednesday, the focus shifts to the future. The planner uses the cleared backlog to generate a draft schedule for the upcoming week. This draft prioritizes the P3 corrective work and the P4 preventative maintenance, the proactive tasks that keep the plant running long-term. Running concurrently each day at 14:30 is a supervisor handover meeting. This daily touchpoint acts as a critical safety net. It allows the team to review any new work identified during the shift and correctly prioritize low criticality P5 tasks so they don't jump the line. Without this structured calendar, everything feels like an emergency. The constant noise of daily operations will cause urgent but ultimately low criticality tasks to consume the labor hours needed for actual reliability work. All of this preparation leads to one specific hour, the Thursday scheduling meeting. This is the ultimate bridge between planning and execution, and the most important event of the maintenance week. This meeting requires mandatory attendance from maintenance, production, and supply chain. Every stakeholder must arrive prepared. There is no time to guess about inventory. Supply chain must bring pre-confirmed parts data, and maintenance must know exactly who is available to work. The workflow is tightly controlled. The team quickly reviews safety updates and past schedule adherence, confirms availability of people and parts, and then reviews the draft schedule. Together, they lock in the specific P1 through P5 tasks for the upcoming week. The primary reason these meetings fail is a lack of discipline. By following a standardized agenda, the meeting remains focused on resource allocation. It prevents the session from devolving into a general grievance forum between departments. The meeting is only successful if it produces one specific outcome, a locked, signed-off schedule. Production must explicitly commit to releasing the equipment at the scheduled times, and maintenance must commit to completing the work. Once signed, the plan is set. Implementing this system requires intense effort, but if you treat work management as a temporary project with an end date, the system will fail. Within 18 to 24 months, operations that drop their discipline regress straight back to reactive chaos. You can track this decay through specific metrics. If your maintenance backlog is consistently growing, your planners are overwhelmed or priorities are misaligned. If your preventative maintenance schedule compliance drops below 90%, your proactive work is being cannibalized by breakdowns. There are also behavioral warning signs on the floor. If artisans self-select their tasks instead of following the schedule, the system is breaking down. Likewise, if work orders are closed in the CMMS without any feedback data or delay codes, your continuous improvement loop has died. The payoff for maintaining this discipline is measurable. Enforcing the 6 steps and protecting your weekly rhythm shifts your entire department away from firefighting. By removing the friction from the workday, the department achieves the output of 5 extra technicians from the same headcount. The tools to find that hidden capacity are already in your facility. Open your calendar right now. Send an invite to your production and supply chain leads and formally establish your Thursday scheduling meeting. The work is already there. It's time to manage it.